Welcome to Rotary Academy YouTube channel, where we present information that helps you improve your understanding and knowledge about power electronics technology and its emerging applications. Today we will be discussing about power diode and their operating principles. Diodes are the simplest power semiconductor device, having only two layers, two terminals, and one junction. Regular diodes have a junction formed by P-type semiconductor and N-type semiconductor. The lead joining P-type is called the anode and the other side lead joining the N-type is called the cathode. Here is the structure of an ordinary diode and its symbol. What is a P-type semiconductor? In a semiconductor crystal, each tetravalent atom creates a covalent bond with four neighboring atoms. In this way, each of the atoms in a semiconductor crystal gets 8 electrons in the outermost orbit. Now, if a small percentage of trivalent impurity atoms are doped in the pure or intrinsic semiconductor crystal, then the electrical behavior of the crystal is drastically changed. Now 3 valence electrons of each trivalent impurity atom create covalent bonds with 3 neighboring semiconductor atoms. In this way, each impurity atom gets 7 valence electrons at the outermost orbit. But still, there is a lack of 1 electron in the outermost orbit of the impurity atom. In other words, there are 3 complete covalent bonds and 1 incomplete covalent bond with 1 electron. Hence, there is a vacancy for 1 electron, and we refer to this vacancy as a hole. Each hole gets created from 1 impurity atom. So far we have explained the creation of holes, but did not focus on how a hole associated with a static impurity atom can move in the crystal. But in a semiconductor crystal, holes can also move like electrons, but the mechanism of movement is different. When one hole that is 1 incomplete covalent bond is created, it will not remain incomplete lifelong. Hence, the total number of holes in a P-type semiconductor is a sum of holes due to trivalent impurity atoms and holes generated due to thermal excitation, whereas free electrons are only due to thermal excitation. Hence, the number of free electrons in a P-type semiconductor is much smaller than the number of holes in it. That is why we consider holes as majority carriers, and electrons are called minority carriers in a P-type semiconductor. What is an N-type semiconductor? The most commonly used semiconductors are silicon and germanium. The silicon has 14 electrons which have been configured as 2, 8, 4. Germanium has 32 electrons which have been configured as 2, 8, 18, 4. Both of the semiconductors have 4 electrons at their outermost orbit. Hence, there are vacancies for more than 4 electrons. 4 valence electrons fulfill these vacancies, each of which is from 4 individual neighboring semiconductor atoms. In this way, all atoms of a semiconductor crystal make a covalent bond with the nearest most neighborhood atoms. Ideally, all valence electrons in a semiconductor crystal are involved in forming covalent bonds. Hence, there should not be any free electron in the crystal. N-type semiconductor crystal structure, but this is not the actual case. At absolute 0 Kelvin, there would not be any free electron in the crystal, but when the temperature rises from absolute 0 to room temperature, numbers of valence electrons in the bonds are thermally excited and come out from the bond and generate several free electrons in the crystal. These free electrons cause the conductivity of the semiconductor materials at any temperature higher than absolute 0. There is a method of increasing the conductivity of semiconductors at any temperature greater than absolute 0. This method is called doping. In this method, is pure or intrinsic semiconductor is doped with pentavalent impurities like antimony, arsenic, and phosphorus. These impurity atoms replace some of the semiconductor atoms in the crystal and occupy their positions. As the impurity atoms have 5 valence electrons in the outermost orbit, 4 of them will create the covalent bond with 4 adjacent semiconductor atoms. Hence, the number of free electrons is greater than the number of holes in the N-type semiconductor. That is why free electrons are called majority carriers, and holes are called minority carriers in the N-type semiconductor. Majority and minority carriers in a P-type and N-type semiconductor. What is a power diode? A power diode is used in power electronics circuits. It varies in construction from a standard diode to enable this higher current rating. In regular diodes, also known as signal diode, the doping level of both P and N sides is the same, and hence we get a P-N junction. But in power diodes, we have a junction formed between a heavily doped P+ and a lightly doped N, layer which is epitaxially grown on a heavily doped N+ layer. A structure of a power diode. The N layer is the key feature of the power diode, which makes it suitable for high power applications. This layer is very lightly doped, almost intrinsic, and hence the device is also known as a pin diode, where I stands for intrinsic. The net charge neutrality of the space charge region is still maintained as was the case in the signal diode. But the thickness of the space charge region is quite high and deeply penetrated the N region. This is due to its light doping concentration, as we know that the thickness of the space charge region increases with a decrease in doping concentration. This increased thickness of the depletion region or the space charge region helps the diode to block larger reverse biased voltage and hence have a greater breakdown voltage. However, adding this N layer significantly increases the ohmic resistance of the diode, leading to more heat generation during the forwarding conduction state. Hence power diodes come with various mountings for proper heat dissipation. Characteristics of a power diode. In signal diodes, in the forward biased region, the current increases exponentially. However, in power diodes, high forward current leads to high ohmic drop, which dominates the exponential growth, and the curve increases almost linearly. The maximum reverse voltage that the diode can withstand is depicted by VRRM, i.e. peak reverse repetitive voltage. Above this voltage, the reverse current becomes very high abruptly, and as the diode is not designed to dissipate such a high amount of heat, it may get destroyed. This voltage may also be called peak inverse voltage, PIV. Whenever the diode is switched off, the current decays from the forward current to zero and further continues in reverse direction owing to the charges stored in the space charge region and the semiconductor region. This reverse current attains a peak IRR and again starts approaching zero value, and finally, the diode is off after time TRR. This time is defined as reverse recovery time and is defined as the time between the instant forward current reaches zero and the instant the reverse current decays to 25% of IRR. After this time, the diode is said to attain its reverse blocking capability. Another interesting parameter defined for power diodes from its turn-off characteristics known as softness factor, S factor. Defined as the ratio of times TB and Ta. If a diode has S factor equals to unity, it is known as a soft recovery diode, and for S factor less than unity, it is known as fast or snappy recovery diodes. S factor indirectly indicates the voltage transient that occurs upon the turn-off of the diode. Low S factor implies high transient overvoltage, while high S factor implies low oscillatory reverse voltage. Thank you for watching, and do subscribe to this channel for your weekly videos.